In the name of God, my name is Reza Behkam, and my greetings and respect to the audience of the 12th International Conference on Computer and Knowledge Engineering. My research title is Intelligent Interpretation of Frequency Response Signatures to Diagnose Radial Deformation in Transformer Windings using Artificial Neural Network. As you can see, the distribution of the transformer faults is shown in figure 1. You can see that the winding faults has the 30% of all kinds of winding faults. So detecting winding faults in preliminary stages is of great importance. We have 4 common fault types occur in transformer windings. In figure 2 you can see these 4 common fault types. Radial deformation, axial displacement, disk space variation, and turn-to-turn short circuits are the 4 common fault types. In this study we have investigated on radial deformation fault type. The main idea of frequency response analysis is depicted in figure 3. You can see that if a change happens in the structure of the winding, it will result in changes of values of capacitances and inductances in the equivalent circuit of the windings. And we use 2 important signals to obtain the frequency response. The input voltage signal and the output current signals in the frequency area are used to obtain the frequency response of the windings. Here you can see the schematic view of the frequency response analysis. In figure 4 you can see that we have 2 main approaches to obtain frequency responses: impulse frequency response analysis and sweep frequency response analysis. We used SFRA or sweep frequency response analysis in this study because it gives us more adjustable signals and we can have better resolutions in this method. Our main contribution in this study is in the computer systems. We designed machine learning methods to analyze the frequency response signatures. Here you can see that based on the last SIGRES report released in September 2020, we do not have any standardized code to interpret the frequency response signatures. So lots of investigations have been done in this area. Our research is aligned with this research topic, and we have contributed in this area for interpreting the frequency response signatures. The main contributions have been listed as follows. All parts of frequency response, including real, magnitude, angle, and imaginary components, have been measured and studied. The sensitivity of each part of the frequency response associated with the locations of RD faults have been investigated. In feature engineering phase for data preparation, the most suitable and sensitive numerical indices have been investigated, and they are used to extract appropriate feature vectors from FRA traces. And also we have designed an intelligent interpreter for FRA traces, and we have used artificial neural networks to distinguish locations of R defaults. An efficient evaluation of the classification with k-fold cross-validation has been done. Here you can see the laboratory setup used in this study. The practical setup in figure 6a shows the 1.6 megavolt ampere transformer windings and the impedance analyzer. In figure 6b you can see that the radial deformation implemented on the windings, and also you can see in figure 6c one disk that includes the radial deformation. For having a detailed information about the windings, you can see the specifications of the windings used in this study in table 1. The FRA test results have been shown in this figure. You can see that the both diagrams related to intact and deformed states of the windings, you can see the FRA signatures related to these states. As you can see, the radial deformation in different locations have their own signatures. So the deviations between the intact signature and the defected signatures can help us to interpret the frequency responses in order to locate the radial deformation fault. Here you can see the statistical indices used to extract the feature vectors from the FRA traces. As you can see, we have used cross correlation factor, the CCF, Linz concordance coefficient, LCC, and normalized the root mean square deviation, NRMSD, and fitting percentage or FP indices to extract the feature vectors. The formulations of the statistical indices in this study are as follows. Here the X shows the magnitude vectors of the reference frequency responses or the intact frequency response. Y shows the magnitude vectors of the present frequency responses or the defected frequency response signatures. Xi and Yi are the ith elements of the vectors, and N is the total number of samples in the given frequency region. The structure of the artificial neural network is demonstrated in figure 8. We have designed an artificial neural network in order to classify the locations of R defaults. As you can see, we have 4 feature vectors as input of the artificial neural network, and we have 10 hidden neurons and 3 output neurons allocated to the classes of the locations. And in equations 6 and 7 you can see the relations between the input hidden and the output layers in the artificial neural network. As you can see, we have allocated 3 classes to the locations of R defaults. If you take a careful attention, you will see that double disks from 16 up to 19 are the top double discs. The middle double discs include the double discs from 12 up to 15, and the bottom double discs are the double discs from 8 up to 11. So we have 10 cases with different locations of RD defect, and we have divided the whole frequency region into 4 frequency subbands, as you can see here. Based on the locations of the resonance and anti-resonance points, these 4 frequency regions are obtained. In figure 9, you can see the diagrammatic representation of the proposed method. We used the intact and defected signals, and after that we implemented the numerical indices to extract the feature vectors, feeding the artificial neural network, and after that we detect the R default location. For having a better visualization of the feature vectors extracted from the signatures, you can see that CCF, NRMSD, LCC, and FP heat maps. These heat maps show the values of statistical indices in each frequency subband and also in each location related to R default. And we have the patterns of the faults. The classification process is summarized in figure 11. You can see the flowcharts related to the procedure. After measuring and acquisition of FRA dataset, we labeled the categories and groups related to various locations of our default, and after that we split the entire frequency band into 4 frequency subbands based on the resonance and anti-resonance points in the FRA signatures. And after that we employed different numerical indices to extract feature vectors, and we shuffled the dataset, and also we split the whole dataset into test and training dataset, and we used the trained artificial neural network to classify the dataset, and we evaluated the performance of the classifier with k-fold cross-validation technique, and after that we calculate the accuracy of the artificial neural network based on the equation 8. Here we can see the sensitivity analysis for different parts of the frequency responses. As you can see, regarding each statistical index, the magnitude part of the frequency response is less sensitive than the others, and also you can see the real part of the frequency responses are much more sensitive than the others if you take a look at the locations of the R defaults. So finally we have the results of the classification regarding the statistical indices used in this study, and also the different parts of the frequency responses, and the accuracies of the test results for ANN. And you can see that if we use CCF index to extract the feature vectors from the imaginary part of the frequency responses, we have the highest accuracy for the classification. And also you will see the bolded figures related to the highest values of accuracies regarding each numerical index and the part of the frequency response. To have a accurate evaluation of the whole performance of numerical indices and the parts of the frequency response, we summarized the entire average accuracy considering each index. If you see, the NRMSD index outperformed the others, and also we have computed the total average accuracy regarding each part of frequency response, and we can see that the imaginary part of the frequency response outperformed the others. In figure 13, you can see the structure of the k-fold cross-validation used in this study. Thank you for your attention.